Let me hear lost thoughts.
All right, so we were doing lesson 29, which is modeling with trigonometry. So this is things like SOHCAHTOA, but we're also going to have some things with a sine curve and cosine curve, okay? So we're going to kind of skip through some of these problems. We're not going to do every single one, probably, because a lot of it is review from Algebra 2. All right, so number one, it says a hot air balloon is directly above a straight road 1.3 miles long that joins two towns. Julie finds that the town closer to her is at an angle of depression of 37 degrees, and the farther town is at an angle of depression of 35 degrees. How high above is the ground? How high above the ground is the balloon? So Julie's up here in the balloon, and she's looking down at these two towns, right? And we want to know how high this balloon is. So we want to know h, the height. Okay, so in order to find that, we can set up a couple different, triangles. Okay, so down here, I'm going to put x, and I'm going to put 1.3 minus x. Sure. Yeah, if one of you guys could set it, that'd be fine. All right, so if I was using SOHCAHTOA, I would have to set up two different equations. Okay, so I'm going to have to set up, it's pretty dark. All right, I'm going to have to set up, this angle of depression is actually the same as the angle of elevation. Guys. So this 35 degrees is over here. So I have a triangle that has h, x, and 35 degrees. So what's the first equation I can set up using those three things? What would I use? Sine, cosine, tangent.
35
exactly. Tangent of 35 equals h over x. All right, now we have another triangle. It's on the other side. And it has h, and then it has 1.3 minus x as its length. And then the angle of depression is equal to the angle of elevation, so we have 37 right in there. So for that equation, we're going to say tangent of 37 degrees equals h over 1.3 minus x. Okay, so this is the situation where we have to do a system of equations. We have h and we have x, and we have h and we have x. Okay, so we did one like this in your study guide for the last chapter. But basically, we're going to solve for h. So I would say h is equal to x times tangent of 35, and I would just leave it as tangent of 35 for now. And then for this one, I'm going to have tangent of 37 degrees times 1.3 minus x equals h. So once you have each of those is equal to h, you can set the two pieces together. So I can say that this part is equal to this part. Okay, so I'm going to do that. So I'm going to say x times tangent of 35 degrees equals, and I'm going to distribute tangent of 37 times 1.3 minus tangent of 37 times x, or x tangent of 37 if you want to write it that way. So whenever we're solving for a variable, we want to get all the things with that variable on one side. So we're going to add the tangent of 37 times x over. So I'm going to have x times tangent of 35, but I'm also going to have plus x times tangent of 37. Well, those are just numbers. Just like if I had 5x plus 6x, you guys would know that that's 11x, right? So we're going to add our tangents. But you can't just like add the degrees. You can't say tangent of 35 plus tangent of 37 is tangent of, I don't know, what is that, 72? Can't do that, right? You actually have to find those numbers. So we're going to find those numbers on our calculator. Okay, so let's do tangent of 35. Make sure you're in what mode?
Degrees.
Degree mode, that's right. It's always hard in pre-calc because you have to go back and forth so many times. All right, so we have tangent of 35, and we're going to add it to tangent of 37. So what we have then is like 1.454x equals, and then I can do tangent of 37 times 1.3, so 0.9796. But I'm going to keep those numbers in my calculator. I'm going to divide them out. So when I divide by that 1.454, all that, I get 0.674. Okay, so what that means is that x, this distance, is 0.674. Is that what we wanted in the end? No, we wanted how high was the balloon. So the very last thing, go to any equation that has an h. So we'll go back over here. And we're going to say, well, we have our x value, take our x times tangent of 35, and we get h. So h is going to be 0.472 miles. So that's our answer. So those ones aren't like super fun when you have to do system of equations. I know you guys don't like those, but it is a little bit harder than what we did in Algebra 2. So it's definitely like pre-calc type question. All right, number 2. So a farmer's conveyor belt carries bales of hay from the ground into his barn's loft, which is 7 feet high. The conveyor belt moves at 200 feet per minute. Find the length of the conveyor belt. So this is part A. So this has nothing to do with the 200 feet per minute. So basically we have a triangle, and we know that we have 30 degrees, and we have 7, and we want to find the length of the conveyor belt. Okay, so we can do that. We'll call it x. So we have the opposite. We need to find the hypotenuse, so we're going to do sine. So we're going to say sine of 30 degrees equals opposite over hypotenuse. Do you guys know sine of 30 degrees now without using your calculator? Let's say 11. No, yeah. 1/2. So you just write 1/2 there. And then you can cross multiply if you want. So you get x equals 14. So without even using a calculator, you get that. So that's going to be 14 feet long. All right, now I'm guessing part B asks something about that 200 feet per minute. So let's see. So it says, how many seconds does it take for the bale of hay to go from the ground to the barn loft? Okay, so basically we're traveling that total amount of 14 feet, right? And we're going at a rate of, what did we say, 200 feet per minute. And we want to know how many seconds it takes. So this is one big conversion. So we're going to say 200 feet every minute. Well, how many feet is that per second? So I'm going to change my minutes into seconds. So 1 minute is the same as 60 seconds. So in a single second, 200 divided by 60 is going to be 3.3 repeating feet each second. Okay, so how do we figure this out? We want to figure out how many seconds it takes. What do you think?
Divide that by 14, or divide 14 by that.
Okay, so we're going to take 14 and we're going to divide by that. Do you guys think that's right? Will that give us seconds in the end? It will. Because basically if we start with 14 feet, and then we use its rate, and we say, well, we can go 3.3 feet every 1 second, then you can get the number of seconds out. So what Louis said is he said, take 14 and divide by the 3.3 feet per second. Do you guys see how that's the same thing? Because you're multiplying by 1 second over 3.3 repeating feet. Okay, so yep, so when we do that, so 14 divided by our answer, we get 4.2. So it takes a total of 4.2 seconds.
Can you just use the proportion?
Yeah, you could set it up as a proportion. You can also just kind of think logically about it and say, okay, it's moving 3.3 feet every single second. So how many of those 3.3 feet fit in 14 feet? Does that make sense? 14 divided by 3.3. And that gets how far it's moved in seconds. So you can think about it that way too. All right, so number 3, the angle of elevation from a point on the street to the top of the building is 53 degrees. The building is 60 feet high. How far is the point on the street from the foot of the building? Okay, so we'd set it up like that. Do you all know how to do that problem? Yeah, we've done many of those. So you would set it up as tangent. So you'd say tangent of 53 equals opposite over adjacent. Just the big thing that people will mess up on is they will forget that they need to multiply the x over. So they'll instead like divide the wrong way. And you'll always get answers that don't make sense in the end. You know, if you do it the wrong way, you'll be like, wait, how is it only like, I don't know, if I did the other way. If I divided the wrong way, it would be 0.022. Are you 0.022 away from the building? No, because your angle of elevation would be like 90, you know, 89 degrees, 89.999 degrees if you're super close to the building. All right, so anyway, so we get 45.213 if we did it 60 divided by tangent of 53 like we were supposed to. Okay. All right, so number 4 we'll skip. Number 4 is very similar to the one that we did that was like a mountain on our study guide from chapter 4, do you guys remember? But it still involves a system of equations. All right, so you have to use substitution to solve for x and y. Okay, so we'll skip it for now. We just did one like it on number 1. Okay, so you guys can try it if you want to. But now let's talk about bearing. So this is something that we haven't talked about before. All right, so it says now we're going to try using trigonometry for other applications such as pendulums and navigation. So in navigation, we often talk about something called a bearing. So that's how we talk about what direction we're going if we are on a boat. So a bearing measures the angle that a path or line of sight makes with a fixed north-south line. So the thing that's really weird about bearing is you guys are pros at doing angles from right here. You're like, oh, 150 degrees, that's right here, right? But bearing isn't like that. And that's the most frustrating thing for pre-calc students. Bearing is off of the north-south line. So what we're going to do every single time is if I have a bearing, I'm going to start with a little line to the north-south. And from that angle, I'm going to rotate around clockwise. Not even counterclockwise. Clockwise, 135 degrees. Do you guys get it? So you're going to go here. So if you're traveling on a bearing of 135 degrees, that means that your boat is right here, and your boat is going in this direction. Does it make sense? You go clockwise, yeah. I know. Bearing's weird, isn't it? Because it's like you're trained to do from that x-axis, and then all of a sudden we switch it up on you. All right, a bearing of 220. So we have 220 degrees. Well, we're going to go past 180. How much do I go past 180? Yeah, like another 40 degrees, right? So we're going to be right there. So our bearing of 220 will be right there. So that's like saying you're starting here and your boat's going in that direction, kind of like southwest. All right, and then if I have a bearing of 15 degrees, well, that's just starting off that north-south line. I'm just going a little tiny bit, 15 degrees.
It's just be a water
You like the bearing stuff? You got it down? Yeah, this is your entire final exam will be bearings. All right, so sometimes we refer to these in a different way using two directions. So sometimes you might hear, and I'll try to stick with bearings for your test and for all that, but sometimes you might hear things like south 25 east. And that's the one I always hated when I was in school because I was like, wait, do I go south first? Do I go east first? What am I doing? And it means that you're going 25 degrees east of the south line. So you start out with the south line, right? See that how that was first? So we start out with the south line. And off of the south line, we go 25 degrees east off of it. So it'd be like that. Does that make sense? So what if I wanted to call it, so this is south 25 degrees east. What is its equivalent bearing? Yeah, good job. Yep, it's 155, because off the north-south line, you'd have to go 155 degrees so that you would still have that 25 degrees left to go south. Does that make sense? So it'd be 155 degrees. Okay, so there's lots of different things that you can do for navigation. It's very annoying. This is why, you know, air traffic controllers, this is why they're so stressed. You guys know how they have the most stressful job. Yeah, it's like the most unhappy job. It doesn't matter how much you pay them. They're still unhappy because they're stressed all the time. All right, so simple harmonic motion. Okay, so simple harmonic motion is used for those sinusoidal functions that we talked about, like sine and cosine, okay? So it's going to be used when we talk about something that vibrates, oscillates, rotates, or moves with a wave-like motion. So a point is said to be in simple harmonic motion if its distance d from the origin, that should say from, not form, from the origin at time t is given by either d equals a times sine of bt or d equals a times cosine of bt. Okay, the motion would have amplitude of a period of 2 pi divided by b, and a frequency of 1 over the period, which is always just b over 2 pi. You just flip it. The frequency is the number of cycles completed per second or per minute or per hour or whatever. I don't talk about frequency too often now. All right, so Alex, you own a yacht. I know, I should have said a plane, but oh well. That leaves the dock in Myrtle Beach and heads towards Freeport in the Bahamas at a bearing of 178.6 degrees. The yacht averages a speed of 20 nautical miles per hour over the 428 nautical mile trip. How long will it take the yacht to make the trip? Okay, so let's draw a little sketch. So he's going on a bearing of 178.6 degrees. So just slightly off the center. All right, so he's traveling from here and he's going down like that. His speed is 20 nautical miles per hour. And his distance that he's traveling is 428 nautical miles. Nautical miles, remember we talked about them, they're not quite miles. They're a little bit off. It has to do with the radius of the Earth and all that stuff. You guys remember doing that? All right, so basically, you're still going to do distance equals rate times time. The distance was 428 nautical miles. The rate was 20 nautical miles per hour. So if I want to find the time, I just divide 428 by 20. Yep, so I get t equals 21.4. So it says, how far east and south is the yacht after 12 hours? Okay, so what we're going to do is we're going to draw this little triangle in. It's a hard triangle to draw. It's very skinny. And what is the angle right here at the top? Yeah, it's 1.4 degrees. Do you guys see that? You did 180 minus the 178.6. And we know that it's going a total of 428 miles, nautical miles. And we want to know how far east and south it is. So we want to know both x and y. Usually I put y as the vertical and x as the horizontal. Okay, and we can find those. Just use SOHCAHTOA. That's it. Yeah.
I don't, it says after 12 hours, so it's not 428.
It's not 428. What do you mean?
It's just after.
Oh, you're right. After 12 hours. Oh, I tricked myself, didn't I? Because it's not 21.4 hours, man. All right, so let's figure it out. So instead of 428, what will we have? Yeah, we're going to do 12 times 20, which is 240 exactly. Thank you. So Kyle, can you write your name on the board so I don't forget? All right, so let's say I want to find x first. Then I'm going to use my 1.4 degrees. I have opposite and I have hypotenuse. So I'm going to do sine. So I have sine of 1.4 degrees equals opposite over hypotenuse. And then I multiply it out. And if I want to find y, then I'm going to do adjacent over hypotenuse. So I'm going to do cosine of 1.4 degrees equals adjacent over hypotenuse. So how about the first table? You guys find the sine one. So Julie's table, you guys find that. And Natalie, your table finds the cosine one. Just the two of you, all by yourself. So you guys are going to find x over there, and you guys are going to find y. What did you get for y?
259.92.
Okay, good. And doesn't it make sense that y would be almost what 240 was? Because you're not going very, very much off of, you're almost going directly south. All right, and then what's x? It's going to be pretty tiny. 5.864 miles. So it's tiny. Does that make sense?
Would we have to do one of these problems on?
Sure. All right, so now let's do a simple harmonic motion one, now that we've talked about it. So suppose that a weight hanging from a spring is set into motion by an upwards push. So we're pushing it up first. And then it's going to come down and up and down and up. Ben, you with me? It takes 5 seconds for it to complete one cycle. And it's moving from its equilibrium position to 8 centimeters above, then dropping to 8 centimeters below, and then back to its equilibrium position. Okay, so if I'm sketching a graph, I'm taking the spring and I'm pushing it upwards first, and it's going up, and then it's coming down, and it's going back up, and it's going to keep repeating this. Okay, and it goes up to a height of 8, and it goes down to a height of -8. And it takes 5 seconds total for it to reach the end. So it says find a sinusoidal function to represent the motion of the moving weight. So you guys are getting pretty familiar with all of the pre-calc words. Do you guys remember what the word amplitude means? That's the height or the distance moved from the equilibrium position. So what's our amplitude? 8. That's going to be our A value. All right. What's our period on this one? Yeah, it takes a total of 5 seconds. Okay, so if I want to find the B value, the period is always equal to 2 pi over B. So 2 pi over B equals 5. Can we solve for B? What do we get? So I need to multiply it over for you guys. So we get 2 pi equals 5B, so B equals 2 pi over 5. So if you look back on that last page, I said that our formula is always in the form A times sine of B times T, and we don't have a plus D or anything on the end. And we don't do a phase shift either. It's always starting either where cosine does or sine does. So we're going to have y equals A sine of BT. So our function is going to be 8 sine of 2 pi over 5 T. Oh, I said B. There we go. Do you guys understand that? How I got that? So then C says, use the function from part B to predict the height of the weight after 3 seconds. So after 3 seconds, I don't know, based on our graph, where would you think it is? Is it above the axis or below the axis? It's going to be below, right? Because here's 2.5, so I'm going to guess we're somewhere around here. So we want to know what that height is. So what we're going to do is we're going to plug in 3 for what? T, exactly. So we're going to have y equals 8 sine of 2 pi over 5 times 3. So I get 8 sine of whatever 6 pi over 5 is. And I can find this on my calculator. It's not a unit circle value, you can just divide it by 5. But if I'm putting it in my calculator, what do I need to make sure I do? Radian mode, right? I know, it's the bane of every pre-calc student's test. All right, so it says we're at a height of negative 4.702 centimeters. Which makes sense based on our graph, right? It should always make sense. Okay, do you guys get that?
Okay, so that's the spring stops it back up at that point, right?
The spring is going back down, and then it's getting ready to come back up.
Okay.
That's right there.
Okay.
Alrighty. All right, in the first 5 seconds, when will the height of the weight be 6 centimeters below the equilibrium position? You might use a graphing calculator to assist you. So we're saying 6 centimeters below. So if you're going to be 6 centimeters below, that's going to be in 2 different locations, right? So what I'm going to have you guys do is we're going to graph our function that we had. Whoops, went the wrong way. So we're going to graph y equals 8 sine of 2 pi over 5. You can put an x in there if you want, not t. We're going to graph that for y1 on the calculator. And then for y2, we're going to graph negative 6, because we're going to be 6 centimeters below. So go ahead and do that. So get out your calculator. Make sure you're in radian mode. Do it on camera. Clear. You guys are faster than I am. Did you graph it? Y2 is just negative 6. Okay, maybe your window's messed up. Or maybe, did you do a negative 6 or a minus 6? Okay, zoom 6. Okay. We're just worried about the first 5 seconds. So you can even adjust your window so it's only from 0 to 5, so you don't get confused and find more than you should. So it's going to be these first 2 places where it's along the bottom. It's going to be right here and right here. You're going to see those 2 points? Okay, so let's find those by doing second trace. Did it do it? Okay, so do second trace intersect. Yeah. 2 pi over 5x. So you need an x in there as well. I did 2 pi x over 5 to make it easier. And you highlighted it here? Yeah. So I'll do that in a second. Okay. All right, so did you guys find it? So you're going to do second trace intersect.
It's showing a straight line.
The second one's a straight line.
Well, yeah, I got that one, but like.
Did you forget your x?
No.
You are in radian mode?
Yes.
Okay. So the first one should be 3.7 or 3.175. Okay, and then finding the other one. So you're going to do second trace again. And you can find that one as well. Okay, so that's going to be 4.325. So you can do this by hand as well. Like you could solve the equation 8 sine of 2 pi over 5t equals -6 by dividing by 8, doing inverse sine, and so on. Just know when you do inverse sine, it's only going to give you one value. We talked about that last time. So you would actually need two values that equal whatever you were looking for. Okay, so you would find one with your calculator, and then you'd find the other one by, subtracting from 180 or whatever you need to do based on your picture. Okay, so let me check Julia's out real quick.
Got it.
You got it? Okay.
Why is the t with inside the curve?
Because you have to have sine of like t in there.
Okay.
Like it's not being multiplied yet. All right, next one. So James is on an airplane that is 160 miles north and 85 miles east of the Indianapolis airport. Okay, so let's have the airport be here. And he is north 160 and east 85.
He's on there in it.
Is on an airplane? Yeah, he's in an airplane. Yeah, please don't ride on top of the plane yet. All right, so basically we want to find this theta in here. We want to find this angle so we can talk about the bearing that he's on, okay? So we're going to set it up and we're going to have our theta, tangent of theta, is going to be the opposite over the adjacent, 160. And you can have it in degree mode. That's probably the easiest way when you talk about bearing, to do it in degrees instead of radians. Probably makes the most sense. So we're going to do inverse tangent of 85 over 160 in degree mode. So when I do that, I get theta is equal to 27.979 degrees. Okay, so let's think about it. If I want to find the bearing that he's on, is that the number that I just found? Are we good? Is that the amount that's off the east-south or the north-south line?
No.
It actually is. I kept waiting on you to change your answer. You just kept saying no. It is, so we're good. But sometimes, depending on if he wasn't like east and south and so, or east and north, like sometimes you have to take that and you have to change it into a bearing. Does that make sense? But you're talking about how far you are off of this north-south line. So we're good. You're just opening that angle just a little bit. Okay? All right. And then Emerson. So Emerson's fishing bobber oscillates in a simple harmonic motion from the waves in the lake. His bobber moves a total of 1.5 inches from its high point to its low point, and then returns to its high point every 3 seconds. So we're starting out at its high point. So what does that tell us when we start at the high point? Yeah, we're doing cosine, right? So we're going to start up here, 1.5 inches from its high point, and then it goes down to its low point. Ooh, maybe it's not 1.5 then. So what should it actually be instead of 1.5? Because it's going to go a total of 1.5. Yeah, we need 0.75 for this distance to give us a total of 1.5. Tricky. And then it returns to its high point every 3 seconds. So write an equation modeling the motion of his bobber if it's at its high point at time 0. Okay, so we're going to have a cosine equation. So we're going to set it up as A cosine of B times T. So the amplitude we found, what is the amplitude? 0.75, right? And then B we need to find. So the period is always equal to, for cosine, sine and cosine, it's 2 pi over B. Do we know the period? When's it back to its starting position? After 3 seconds, right? So then we can solve for B. So if I multiply the B over and divide by 3, I get 2 pi over 3. Okay. So our final function is y equals 0.75, or you can write 3/4, cosine 2 pi over 3 t. That's it. Okay. So not as hard as that one. Remember I gave you a Ferris wheel one that was pretty hard one time. So much easier. Yeah.
I think the we should add 180.
Well, the bearing's always off of this north-south line in this direction. Does that make sense?
Yeah, but it's that way.
I don't know what she's saying. So here's our bearing line. And how much are we going to rotate off that line to go in that direction?
Yeah, but
I see. So the pilot wants to fly directly to the airport. So he's, I see what you're saying. So he's already here. Yeah, so you are right. We should go backwards, right? Does that make sense? So we need to figure out what bearing he should go. So that bearing then, that I was thinking that he was already on the other corner and he's going the other direction, but she's right. The airplane is on the far right top corner. Do you guys understand what she's saying? So if you want to find the bearing that we're going, we just kind of rotate around. So the angle we found was 27. So you were right, Yaya, when you kept saying no.
You see?
That was 27 something. That's really,
I think I should get an extra.
that's really right here. So you need to add another 180 degrees. So if I add 180 degrees to that,
why are you so
Because, like, I knew something was wrong with that.
then we get, no, I'm sure. I am questioning. All right, so we get that. Does that make sense?
I feel
It's number 3 because he has to go backwards. The plane is over here,
but technically,
and he has to go in this direction to get back to the airport. Here's where the airport is. So you're right. Thank you. Can you put your name on the board, please? All right, we'll put at the end of that section.
I give up. I was speaking to
you? Oh my God.